Thanks for joining us again. In this video, we're going to talk about the mathematics of chemistry. I think oftentimes when a student is introduced to chemistry, an intimidating factor about this subject is how much math seems to be involved. It is a very quantitative science, and it's one in which we have to measure uh, pretty much everything that we do in the laboratory is some sort of measurement. So the math that we see in a chemistry class is a little bit different than the math that we're used to from our mathematics classes. If I had a bowl of tomatoes like the one on the screen here, and I asked you how many tomatoes are there, you could count them. And if I pass that same bowl of tomatoes around the entire classroom, everyone would count them. Everyone would come up with exactly the same answer. Because when you count things, you can know things exactly. You're not going to be one off. You're not going to have one too many. You can, at a young age, learn how to count and know things exactly. But when you measure, which is what we primarily do in chemistry, there's always a little bit of error associated with any measurement, no matter how good the tool is that you're using. So, for instance, if I said, what's the distance between this white line right here on the football field and this white line over here? You might say, well, that's 3 yards. And I would ask, how do you know that? How do you know that it's 3 yards? And you might say, well, someone measured it. And you're right. Someone did measure that. But how good was their measurement? And how do you judge that? Did they get a ruler out or a meter stick or a yardstick? How was that measurement taken? And there are varying degrees in how precise a particular tool might be. So your neighbor might have a yardstick that measures only yards. It can measure 1 yard at a time. You might have a yardstick that actually measures in inches and feet, and you can make a more precise measurement than they can because you have more precise divisions or marks on your particular yardstick. So I think what I'm trying to get at is anytime you make a measurement in a science class, there's always going to be a little bit of error associated with it. I can't know something exactly. If I sent you all out to the football field to measure those 3 yards, you would come up with somewhat different answers, especially if you were trying to do it precisely. So in chemistry, the other thing that we have to think about is how do we measure? What's the language that we use for measurement? What are the standards that we use? And within the scientific community, the standard is the International System of Measure, which is sometimes referred to as the SI system of measurement. And it's essentially the modern version of the metric system. So it's one that is a little bit familiar to us in the United States, but within the scientific community, it's pretty much all we use. So we have to do a little bit of translation. Even though I'm a cross-country coach and my runners run 5 kilometers, I still think of that in terms of miles. And so that translation aspect is a little bit tough. We're going to look at 4 of what are called the base units that make up the SI system just briefly. There are actually 7 base units. We'll eventually use 5 of them in this class, but just to get started on the year, I think there are 4 that we need to be aware of. All of the base units, like this one for length, all of these base units are now defined on some constant. So, for instance, you might have heard of the speed of light. Speed of light travels at a constant speed in a vacuum, and these particular base units are defined on those or based on those constants. We're not going to get deep into the constants. I would be remiss if I didn't say up until very recently, many of the base units were actually defined on a real object that you could go and visit. So, for instance, up until not too many years ago, you could go to France and visit the meter, like the only one, the real deal, the meter stick, if you will, and you could compare maybe your meter stick to the meter stick found in, or to the meter, to make sure that it was accurate. So I don't have a meter stick pictured here. Obviously, I have a recreation of a ruler of sorts, and it looks like it's probably supposed to be in centimeters, but I've blown up the picture so they're a little bit bigger than they should be. I do want to teach you a little bit about how we go about measuring things. So I should say first, our base unit, if we want to measure the length of this block of whatever it might be, let's say it's granite or something like that. Our base unit is the meter. The symbol that we use to measure it is a lowercase m. But when we make a measurement, and this is something we'll get a lot of practice with in the lab, when we make that measurement, we have to make that measurement in a very precise way. So if I look at this seems to start right at 0 centimeters. And right now, the edge on the other side seems to be between 1.3 and 1.4. So there are rules about this in measurement. And the rule that I'm going to introduce to you right now is that when I'm making a measurement, I actually have to go always 1 decimal place beyond what I know for sure. So what do I mean by that? Here, I know this object on its side is 1.3 something centimeters. I'm going to write centimeters off to the side. It's somewhere between 1.3 and 1.4 centimeters. I'm going to make a guess that it's about 1.38 centimeters. And this digit right here was exactly what I just said it was. It was a guess. But making good and valid measurements always means taking a guess in that last digit. And your guess might come up to be a little bit different than mine. Remember what I said earlier. There's always a little bit of error involved when you make a measurement, and that's where that error comes in. So we can measure length, and we could expand into something like area by measuring 2 sides of this, or if it were a 3-dimensional object, we could measure volume. We'll talk about that on another day. Our second base unit that we're going to talk about is mass. We think about mass, I think we often think about weight. They're a little bit different, right? Weight is something that can change if you go from, say, here on Earth to the moon, because weight has to do with how the force of gravity acts on the object. When I look at mass, it's independent of gravity altogether. Now, they're directly proportional to one another, but mass and weight are a little bit different. Mass is really defined as how much matter is contained within an object. And so this is a picture of what used to be one of our standards. Like I said, you could go into a building in France and find the meter stick. Well, you could go into that same building in France and find the kilogram, and it would have looked just like this. I think this is actually a picture of a copy of the actual kilogram in France. Now it's no longer defined that way. It's defined based on a constant of nature. So the kilogram, it's about 2.2 pounds, just for those who are curious. And one thing that I think is a little bit weird about this base unit is that it actually has a prefix on it. So kilogram means actually 1,000 grams. You might think that gram would be the base unit, but for whatever reason, we use kilo instead, maybe because a gram is so small. Our third, we're going to talk about this one probably the least. It's the most familiar to us. When we measure time in seconds. We use that here in the US as well. The symbol, of course, for the second is a lowercase s. And this is a picture of a clock, a very good clock. Probably, I think this picture may be of kind of a world record setting clock. These clocks that look like this are what are called atomic clocks. The second is defined based on something called the frequency of a hyperfine transition of an atom of cesium, which is one of the elements, a really kind of out there definition, one that you don't have to worry about. But that's how it's defined. And, if you find a clock like this, they're incredibly accurate. In my car, I lose, it seems like, a minute every month. I have to kind of adjust the clock so it's back on track. These clocks, these atomic clocks, are so accurate that they lose a second, over the course of 1 billion years or 3 billion years or something like that. So super accurate clocks. And finally, the last one we're going to talk about, temperature. I got a picture of a Celsius thermometer over here on the left, but temperature scale that we use for the SI system is Kelvin. Talk about why in a minute. Thinking back to measurements, if I wanted to measure the temperature here and I'm reading this level against this scale, it looks like it's right at about 23. So I might write 23 degrees Celsius. But if you were paying attention earlier, I actually want to guess one digit past what I know. So it looks like it might actually be a little bit above 23. I might write 23.1 degrees Celsius. So Celsius is what we measure temperature with in the lab often. But it's technically not our standard or our base unit. We choose Kelvin instead, which is related to the Celsius scale, but it's an absolute scale. What I mean by that, you may have heard of the term absolute zero, and absolute zero kind of represents the lowest temperature that is theoretically possible. And so there are no negative temperatures on the Kelvin scale. And that's why we use that instead of Celsius. It turns out when you have a scale with negative temperatures and you start to do calculations, things get a little bit weird. And so we use this Kelvin scale instead. You'll note that we don't use the Fahrenheit system at all. It's pretty strange, even though we're accustomed to it here in the United States. Just to give you a sense, this temperature right here is not far off from a room temperature. Maybe a little bit lower than that would be a room temperature. And of course, like boiling water happens at 100 degrees Celsius, 212 Fahrenheit. I really, a lot of teachers will ask their students to know the conversion between Fahrenheit and Celsius. I usually don't, just because we don't actually use Fahrenheit ever in this class. One conversion factor that you will want to know is that Kelvin is equal to Celsius plus 273. It's really 273.15, but this is good enough. That's maybe our first equation for the year. So if I am at, let's say, 0 Kelvin, that means it would be a temperature of what? Negative 273 Celsius. That's the lowest temperature that's possible. One day we'll talk about why that is. Okay, so those are the 4 base units that we're going to use often, at least in the beginning part of this class. We'll see you next time.